Okay, hi everyone. So let us do the brainstorming for today. So for this PFD, I saw that you use the heat exchanger here. So why do you need the heat exchanger over here?
Because we want to preheat first our reactant before enter to this reactor.
Okay. So what is the temperature difference over here?
This one from the reactor is 25 degrees Celsius, and for the condition in the reaction is 30 degrees Celsius. So that's why we preheat the reactant first.
Okay. So what can you comment on this operating condition before entering the reactor?
The operating condition will be 30 degrees Celsius with 1 ppm.
Is it optimum enough?
Let me check first.
Okay. So can you check? What do you think? I mean,
I think if 30 degrees Celsius is just like a minimum condition.
I
So
see.
maybe we should increase it more for it to become optimum.
Okay. So please check. I think you need higher temperature prior to entering the reactor because based on the principle of heat exchanger or heat transfer, so when you enter at lower temperature, the reactor temperature will also drop. Okay, so please check on that, and also whether the operating pressure is high enough. So 1 atm is our ambient pressure. Okay, so please check on that.
So we could check on that.
Okay, so this is the heat exchanger that you used to design for
That's true.
this one, right?
Yes.
So which layout do you use here?
I use the 1 to 2.
Okay, so why specifically you use 1 to 2? Because the simplest one is 1 to 1, right?
Because 1 to 1, according to our calculation, 1 to 1 does not achieve the required heating that we want.
Okay,
So we use 1 to 2.
so how can we know that this is 1 to 2 layout?
Because there is like 2 passes for
Okay.
U-turn in the heat exchanger.
Okay, so 1 U-turn give us 2 passes.
Yes.
Alright, so very good on that. And what is the important criteria that you realized during the design of this heat exchanger?
Maybe it's the bundle diameter clearance.
Okay.
in heat exchanger.
Okay, so maybe could you please sketch something on that?
Okay, so something like the diameter there, and then the graph is something like this.
Okay. Right. So what happened if you have your value last time your value was smaller, right? Because you extrapolate the bundle diameter clearance. So what happened?
I think our bundle diameter clearance, if according to the graph in the textbook, is ours is like out of the graph like smaller than the range lah.
Okay.
So I think they extrapolated it because
Okay.
it looked like linear, so we extrapolated.
Okay. So is it possible to do that?
Theoretically, I don't think it is.
Mathematically it's suitable, but when we want to know the physical meaning of it, so what happened to the bundle diameter clearance if you extrapolate out of the graph here?
Maybe because the difference is quite small and no space between the diameter of bundle with the tubes here.
Very good. So please be careful. If your answer is out of range, so that means something is not right over there. Okay. So I think you have improved from the previous calculation, so that's very good as well. And one more thing, is this triangular or square pitch arrangement of the tube?
It's triangular because
Okay.
you can see that there is many triangles.
Okay. So any advantage of triangular compared to the square pitch?
Because of space.
So
Because of space. So
which
Then
one
will
is
be more, the heat transfer will be more efficient if there's more space compared to
compared to
compared to the square one.
The
Square one limited space.
Okay. Right.
Yeah.
Okay, so I think that should be it for today. So good job on improving the calculation, and please check on the optimum operating condition for the reactor.